All right, everybody, in the last video, I said you've got an example problem. Go try it and see what kind of number you get, and then watch the next video to see if you got the correct answer. And I know that you tried it. I know that you took the time to go through the motions and solving this problem on your own. And you're going to watch this video and you're going to say, I got the correct answer. I know how to do math. And then I also know that you're probably going to be lying because most of you are not going to do this example problem on your own. So shame on you, because here's an example to figure out whether or not you are setting the problem up the correct way. So here was the example problem, and it says the mass of an empty 25 milliliter picnometer is 35.2341. An analyst uses it to measure the specific gravity of a raw material. Ooh, sounds so fancy. After filling the picnometer with water, the mass is 60.4143. Once emptied and dried, the raw ingredient is added, and that mass was 56.2941. Calculate the specific gravity of the substance. Okay, so basically what's happening here is that we are once again doing method 1 that can be found in the USP. And this was method 1, all of the scribbles. Oh, but this was a picnometer method. So we have taken a very clean and dry picnometer and obtained a mass. And then after that, we filled it with water to the rim. We pushed on the top, squirted all the extra juices out of it, and then we took a mass and we recorded that mass. And then we emptied all of that water out of there. And then what happened is that we dried it, made sure it was clean, and then we added our sample back onto it. And the sample, once again, we took it to the top. And when we took it to the top, we put the stopper back on it, and it squirted out all the sample that we didn't need to have. It was all the extra. We wiped it off, and we took another mass. So that is the example problem that we are focused on right now. All right, so how on earth do we do this type of example problem and calculate specific gravity? Because for the first time here, it's actually telling me to calculate the specific gravity of a substance. So that's what we're going to focus on, and I'm going to show you how easy this is going to be. All right, so the empty picnometer, I'm just going to do PY for picnometer, was 35.2341. And then the picnometer plus the water that filled it up, we took a new mass, and that was 60.4143. And then the picnometer that has been cleaned and dry again, but this time instead of water, it's got my sample. That mass is 56.2941. So we need to go through the motions of solving for specific gravity here. We're going to do this two different ways, and we're first going to do density, and then we're going to actually go through the motions of what the USP&F tells us to do as far as their calculation goes. All right. So the first thing that I probably want is the mass of the just water that is contained in that picnometer, and then the mass of just the sample that is contained in that picnometer. That's really kind of our first step, no matter which way we decide to solve this. So this is a very simple subtraction problem. That's all that this is. So what will happen is that if I want the mass of just the water, I'm going to take the mass of the water and the picnometer together, 60.4143, and I'm going to subtract the mass of just the empty picnometer that was cleaned and dried. So 35.2341. All right. So this is the mass of the water that is contained in the picnometer, 25.1802. All right. So 25.1802 grams. Next up, I'm going to do the same thing with my sample. I need to know how much this sample weighs once it gets filled in the picnometer. So I just do this the exact same way. I take the picnometer that's now holding my sample, and that combined mass is 56.2941. And then I'm going to subtract the mass of the just empty cleaned picnometer, and that was 35.2341. 0.841. All right, so the mass of the sample is 21.06. All right, so 21.06. And I'm just going to add a few extra zeros. All of our masses have 4 digits after the decimal here, and I did a addition or subtraction problem. So I probably want to match that, and I want to keep those 4 digits after the decimal. If you don't, it doesn't affect your calculations. But just being me, of who I am, I'm going to keep them. All right, so now I've got the mass of the water, and now I have the mass of the sample. So what we've talked about, really, for multiple videos now at this point, is that in order to calculate specific gravity, you need density. All right, so density is going to be calculated by grams divided by milliliters, right? That's what we said. That's how we calculate density, especially if it's for a liquid. We take the mass and we divide by the volume or space that it takes up. And in each one of these, the example problem told me that this was a 25 milliliter pycnometer. This pycnometer is made to hold, as close as it can, 25.000 milliliters of liquid. Whatever liquid that might be, that space is 25 milliliters. So if I wanted, I could calculate the density of the water, and I divide by 25, and the density of the sample. So I divide by 25. Now I can put 25.00000, but when I put 25.00000 into the calculator, it's not really going to affect my number at all, my final calculation at least. All right, so I'm going to take 25.1802 and I divide by 25. And the density of water is not 1. This density of water is 1.007 and 2, and we can round it off from there. All right. Next up, I'm going to do the same thing with my sample. I'm going to take 21.0600 because that is the mass of that 25 milliliters, and we'll divide by the volume that it takes up because that's 25. And this mass, or this density, is 0.8424. So this is the density of the sample, and this is the density of the water. All right, now I know that I used lowercase d for density. Shame on me! I thought you were writing capital D's this whole time. Yes, but shame on you, because density is rho. Density is not capital D, and density is not lowercase d. But we know what the little d stand for. We know what the big D stand for, so it's okay. All right, so here we get 2 density values, one with my sample, one with the water. And now to calculate specific gravity, what's going to happen is that I need to come over here to the side, and I need to say, oh, specific gravity is the capital G. And to do this, I'm going to take the density of my sample, which is 0.8424, and I divide by the density of water held at the same conditions. So see, doesn't that make me sound really smart? So 1.0072. So the sample divided by the density of water. All right, so when I calculate G, that's going to be my specific gravity value. Again, it's just a division problem at this moment. So 0.8424, and then I'm going to divide by 1.0072, and then I hit enter. And what I'm going to find out is that the specific gravity makes this number change a little bit, right? Because I did not divide by 1 exactly. So I took 0.8424 divided by 0.10072, because that's really the proper number. And then my specific gravity is going to end up being 0.8364 if I want to round it off. So 0.836 and 4. Specific gravity, keep in mind, has no units, and that's because this density value was in gram per mil. This density value was in grams per mil, and we chop that off because they cancel each other out. Units do when you take them and divide them that way. So 0.8364 is the specific gravity. 0.8364 is the number that we would report in real life when we make these types of measurements. And 0.8364 does correspond in a very strange roundabout way to density values if you go through this motion and solve for the densities first. Okay, so there's one way to solve this problem. Now, the other way to solve the problem, and that what you'll find in the USPNF, is that, once again, we talked about this in the last video, they don't necessarily make you go through the motions of dividing by 25 every single time. And the reason they go through the motions of not dividing by 25 every single time is because you are assuming that these measurements are being made with the same, I'm going to say that again, same pycnometer. That's what we're after. If you use different pycnometers, this is not going to work, because different pycnometers, they are made in a different way. They slightly weigh something different. They slightly hold a different type of volume, and your numbers are not going to be as good. So you need the same pycnometer when you make these measurements here. You cannot take one pycnometer and measure water and another pycnometer and measure your sample and compare those two. It's not going to work out for you quite well. So if you follow the USPNF, they are assuming that the 25 is the exact same in the bottom, which means the pycnometer is the exact same that you have used. So if you do that, in a sense, they're going to cancel each other out, right? I used one pycnometer here, and then I emptied it and cleaned it, and I used the same pycnometer here. So if I divide by 25 on this side and divide by 25 on that side, I'm going to get different numbers for densities. Yes, absolutely. But that 25 really doesn't make a big change in what we would call the overall calculation. So if you go to the USPNF and you take a look at that document again in the general chapter for specific gravity, what they're going to tell you is that they're going to say, hey, to calculate specific gravity, we're going to make this a little bit easier for you, because we don't want you to go through the entire motion of calculating a proper density value, because in the end, we know that that's not really going to make a difference. It's just extra work. It's just extra math, because we are assuming you are using the same pycnometer for this. So what they tell you to do is they tell you to take the mass of the pycnometer and the water together and subtract the empty pycnometer. Okay, well, we did. We got that value. It's right here. And then they say, take the pycnometer and the sample and that mass, subtract the empty pycnometer weight from it that's been cleaned and dried, and you'll get that value. And they're going to say, take the masses of these two, not the densities. Take the masses and divide them. What happens is that this saves you an extra step. So to calculate specific gravity according to USPNF, well, you don't need to go to the density value. You're assuming the same volume, which really cancels each other out. And the only thing that you've got to do is take the mass of the sample and divide it by the mass of the water that pycnometer holds. And then we're going to divide those two values together, and ta-da! We get 0.8364, the same exact answer as if we fully calculated a darn little density value for each one of these. So specific gravity can be calculated in a laboratory without the need of a proper density number. The only thing we need is the mass of the sample held in the pycnometer and the mass of the water held in the pycnometer. And when we do that, we can divide them and we get a specific gravity number. So, ladies and gentlemen, this is method 1, and this is how we calculate specific gravity by hand if we had to do it in a laboratory and report those numbers. Once again, we rarely ever talk about reporting density values. We talk about reporting specific gravity values instead. So here's the general chapter 841 for specific gravity in the USP. You've seen this before. I've showed it to you already. You probably even have a photocopy of it by now. And then if you scroll down and you take a look in the middle of the first page, under method 1, when it talks about the pycnometer, it gives you this nice little pretty equation, and right here it is in the middle. So it says the specific gravity, and they even use a lowercase d, not a g, and the specific gravity is going to be equal to the masses of your sample and the pycnometer subtracted, divided by the masses of the water and the pycnometer. And you're going to divide those two things, right? So that's how they calculate specific gravity. That's really kind of the method that they want you to follow through. But by definition and by what you've been told in other maybe science courses, yes, you can go to density and you can divide by the volume of each one of those and then divide those densities with each other and get specific gravity too. It's extra work, it's extra steps, and you're using the same pycnometer, you should be at least anyway. So this is going to be a shortcut in order to calculate that value for you. All right, so as we go down, you're going to see method 2 that shows up after method 1. So we want to talk about method number 2 before this video is over. And method number 2 is if I'm feeling lazy and if I don't want to go and get a pycnometer and I don't want to go through the motion of cleaning and drying and cleaning and drying and filling and squirting stuff out of the top and wiping it all off, then I can choose to use method 2 instead of method 1. And method 2, like many of the general chapters, they always include some type of automation, some type of technology, chemical technology, ding, 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 that we can use to make our job a little bit easier and make it a little more automated, especially if we've got to do multiple samples of these. So an instrument is going to be the focus of method number 2. And the instrument will have, according to the USP, a U-shaped tube that will contain the liquid that you're trying to do the specific gravity of. That tube will oscillate, and the way that it oscillates corresponds to the density of that material that you have injected onto the density meter. So they'll take that density value and they divide by the density of water, because it knows what the density of water should be at the temperature that you make your measurements at, and that is how it calculates the specific gravity for you. So method number 2 does go through and it leads to the density value. The instrument is measuring the density of the sample. The instrument knows the density of water at that temperature that you're making the measurement in, and it's taking those two densities and it's dividing them. And that's how it's calculating the specific gravity for you. So on the report, what you will find is a straight up density read. It gives you those because it's going through the motion to do it anyway. So it's going to give you that data. And then down at the bottom, you're going to see a specific gravity number as well, or somewhere else on that report. So it does give you both, and that's the reason. It's going through the motion. It's got to have that number anyway, so it's going to report that number to you. This term oscillates. What does that even mean, right? What is oscillation? Well, oscillation almost means like a pendulum, back and forth, back and forth, back and forth, back and forth. It's a repeated motion that goes on. And then this oscillation, this back and forth, back and forth, back and forth, is a way that the instrument knows, okay, this is how it's moving. This is how it's moving back and forth, back and forth, back and forth, back and forth. So therefore, this corresponds to this density value because the density meter is made that way. So the density meter is looking at the pendulum swings, maybe of that U-tube, maybe if that's what you want to think of it as, and it's correlating that to a density value based on internal memory standards and calibration. Here is a very simplistic little density meter. These things can be as fancy as you want them to be, but this is just kind of a laptop bench model, nothing connected to a computer, nothing connected to a software. Just inject your liquid in there, and that liquid is going to be measured, and the density meter will pop you out a number for density. It also will pop you out a number for specific gravity too, but density is going to be one of those things that it's going to definitely do and provide to you. The USP monograph also says that we have to do this 5 times. So there's a little bit of statistics that's going to be involved there. So if I pull up this method number 2, this procedure, the use of an oscillating transducer density meter, and the apparatus consists of the following: a U-shaped tube, usually of borosilicate glass, which contains the liquid that you want to examine. And then a blah, 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 that measures the oscillation, and then a blah, 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 that measures how it oscillates between constants and times, and then a blah, 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 temperature correction, because temperature is going to play a role in the density values as well. So it gives an equation that the density meter is using, not that you're using, and then blah, blah, blah. And then it provides the specific gravity because they are taking the density of the sample that they have designated as L, and density of water that they have designated as W, and they are dividing the densities by each other. Keep in mind, it says both are determined at 25 degrees most of the time, just like our hand measurements, 25 degrees, unless it tells us otherwise in the monograph. If it does, then we key in that temperature value to the machine. We don't worry about heating it up on a hot plate. We don't worry about heating the pycnometer up that contains the sample. We literally key the temperature into the density meter. That will heat up or cool down to what it needs to be, and that's where the measurements are going to take place. And then it talks a little bit about the calibration here, and it talks about the procedure here. All right, so a little bit more about the calibration, the validation piece, and so forth. First, before I go through that method, what we have in the chemical technology lab currently is a Rudolph Research density meter. So this one's a little bit bulkier, a little bit bigger than the one that you've seen before. But there is a live view on the screen of the density meter, and you can actually watch the sample slowly go into the YouTube, and then it circles around, there it goes around the curve, yay, and then it slingshots, and then it comes all the way back through. So we got to make sure that we fill up that YouTube. If we don't fill the YouTube up, then we're not having the appropriate amount of sample on the inside. So when we inject sample into the density meters, we want to make sure that we inject enough sample where a little bit starts to come out of the machine. It's always better to overfill it than to underfill it, and the overfilling is not going to cause a problem because there's a nice little waste jug back here in the back that's going to collect all of that filthy little trash that comes out of it. So it's always better to overfill for that reason. You're not going to hurt anything by doing that. So the sample goes in, typically through a syringe, and this syringe you're seeing kind of up and down because this is a slightly different model than what we have in our laboratory. The one that we have in our lab has the syringe and it goes from the side. So it pokes out from the right-hand side, not straight up and down like this one does. So you'll insert the sample, you'll overfill the U-tube, and then there is a temperature setting that you will put into the computer software on the instrument mainly, and you'll key that in at 25 or 35 or 40 or 20, whatever you need, and then it will heat up to where it needs, and then it will begin to make the measurements at that temperature setting. What you're seeing on the screen is a density value that happens up here at the very top of these instruments, and then below that, or nearby at least, they do have a specific gravity read that will show up as well. So that is the Rudolph Research Density Meter. This is what you will be using when you do specific gravity in the laboratory. We also go through the pycnometer motion. We want you to go through that as well to get some training on that, how to use it, what's its purpose. But a density meter is also something that we talk about and that we use because you could find that in a main working laboratory out there. Finally, we have to validate the machine. We have to make sure that the machine is actually working the way that it needs to work. And we've got to have proof in the pudding that, yep, we checked it. It's looking good. It's registering the right density numbers. We're not going to question any of this data at all. So in order to make sure that this instrument is actually working the right way, they will often go through a validation procedure. Not necessarily a calibration, because a calibration is making adjustments on the machine to make it read what you want it to read. This is more of validating the data. So validation is happening here. So what's happening is that we will inject normally air, and air will be injected at 20 and air will be injected at 25. So literally nothing in the YouTube channel, nothing in that machine other than air. That is it. So we're going to heat it up at 20 and we take a density, and we heat it up at 25 and we take a density. And those will have density values that are acceptable, and they give you a window of what is acceptable. They know you're not going to be perfect every time, so they'll give you a little bit less and a little bit more, and they'll say if it falls in this window, then you're going to be pretty good. I think that you're going to be okay. Next up, after we do that two-stepper, we then inject just straight up water. This should be distilled water. So distilled water does not have anything at all in it. No ions, nothing to weigh it down, nothing to add to it, no bacteria, no contamination, nothing. So we want distilled water preferably. We use deionized water though. It's not perfect, but it does a pretty decent job. And then that water is also going to be measured at 20, and that water is going to be measured at 25 as well. So yet again, we have two more points that we are referring to. We know what those density values should be, and those should be provided within an acceptable window. So we go through this motion every time we use the density meter or on a scheduled routine basis, and we create a log, and we make sure that this instrument is in line with what we should be seeing, and if it ever goes out of wacky, then someone's got to come in and someone's got to fix that a little bit better for us. All right. Finally, you want to make sure that the water is also degassed, and degassed water samples, CO2, always a problem. So by heating that up a little bit, you're driving off all of the CO2, because that gas can create bubbles, and bubbles take up space, and space is going to be a problem. So the density of water at 25 degrees, which is pretty standard, should be 0.9970. So if I did water at 25 degrees, I hope that I would get 0.9970. And if not 0.9970, plus or minus at least an acceptable window around that value. Finally, repeatability for these instruments, they need to be plus or minus 0.0001. So we're talking about standard deviation here. So if it makes multiple density reads, we want to make sure that the standard deviation is appropriate. We want to make sure that the instrument can do the same value every single time it makes a reading, and repeatability is the word that we use for standard deviation. So we want these numbers really close together, and that is why that these density meters will often do 5 measurements of density. It calculates an average. It gives you that average, and the average is what we're looking at for acceptance criteria. And then it's also doing 5, because by doing 5, it can calculate a standard deviation, and that standard deviation is going to be given to you on the report, and we hope that that standard deviation is 0.0001, give or take a little bit. All right? So that's the story with specific gravity, USPNF, method 1, method 2, and if we use method 2, how do we ensure that this instrument is providing appropriate numbers, right? This instrument is expensive. This instrument is not very smart. It's kind of stupid. So we got to make sure that it doesn't have a stupid day. And by validating it and going through the motions of running 2 airs at different temperatures and 2 waters at different temperatures, if all of those check out, then that means this density meter is performing according to plan. Nothing needs to be cleaned. No fine adjustments need to be made. So the data that's popping out onto my screen actually means something. And that's what the validation is all about. You don't want to take instrumentation for granted. So we've got to double check it, just like we double check everyone else that works in the lab. And this is part of that process. All right, so with that said, I think that I'm done with specific gravity, General Chapter 841. So, of course, there's going to be a lecture assignment that follows this, talking all about some background and density and specific gravities and math problems and example problems. So make sure that you have your calculator ready, because you're probably going to need them in some of those questions. And until the next General Chapter, I'll see you then, but good luck on 841. Make an A!